What you're watching right now seems impossible. A swarm of autonomous drones, each equipped with precision extruders, depositing layer after layer of specialized concrete while hovering in mid-air. No cranes, no scaffolding, no construction crews climbing through skeletal frameworks. Just machines working in perfect coordination, building a house from the ground up in 8 hours. This isn't science fiction. This is the future of construction, and it's being developed right now in research. Labs and prototype factories across 3 continents. The global housing crisis has reached a breaking point. In the United States alone, we're short approximately 1.5 million homes. The construction industry loses an estimated $10.8 billion every single year due to skilled labor shortages. In 2024, that shortage resulted in 19,000 fewer homes being built than the market demanded. The average construction project now takes nearly 2 months longer than it should because builders simply cannot find enough workers. And here's the number that should terrify every economist and policymaker. The industry needs to hire roughly 439,000 additional workers annually just to meet current demand. Workers who don't exist, workers who aren't being trained, workers who chose different careers because nobody told them that laying brick could pay $38 an hour. Traditional construction methods haven't fundamentally changed in a century. We still stack materials by hand. We still rely on armies of specialized tradespeople who spend decades mastering their crafts. We still accept that building a single-family home takes 6 to 11 months. But what if we could compress that timeline from months to hours? What if the solution wasn't finding more workers, but reimagining the entire concept of how buildings get made? The answer began taking shape in 2022, when researchers at Imperial College London, the Swiss Federal Laboratories of Materials Science and Technology, and a consortium of universities, including University College London and the University of Pennsylvania, published a groundbreaking study in the journal Nature. They had created something the world had never seen, a coordinated swarm of flying robots capable of 3D printing structures while in flight. They called it aerial additive manufacturing, and it changed everything we thought we knew about construction's physical limitations. Professor Mirko Kovac led the team from Imperial's Department of Aeronautics. His inspiration came from an unexpected source: bees and wasps. These insects build massive, architecturally sophisticated structures through collective action. No single bee designs the hive. No individual wasp directs the construction. Instead, they follow simple rules, communicate constantly, and adapt in real time. Kovac asked a radical question: could flying robots do the same thing with concrete? The system they developed uses 2 distinct types of drones working in concert. BuilDrones carry the actual printing payload, depositing material through precision nozzles during flight. ScanDrones act as quality control inspectors, continuously measuring the BuilDrone's output, tracking progress against the digital blueprint, and relaying adjustments to keep the structure within tolerances. The drones communicate with each other and with a central mission planning framework developed by UCL's Autonomous Manufacturing Lab. They are fully autonomous in flight, though a human controller monitors the process and can intervene if necessary. The physics of making this work seemed nearly impossible at first. A drone moving through air is constantly adjusting, compensating for wind, correcting for drift. How do you achieve construction-grade precision from a platform that's literally floating? The breakthrough came through the development of specialized manipulators mounted beneath each BuilDrone. These delta arm systems, similar in concept to the print heads on desktop 3D printers, can compensate for the drone's movements in real time. As the aircraft pitches or rolls, the manipulator adjusts in the opposite direction, keeping the nozzle precisely where it needs to be. The proof of concept structures they built demonstrated remarkable accuracy. manufacturing tolerance of just 5 millimeters. That's roughly the thickness of 3 stacked credit cards. They printed a tower over 2 meters tall using 72 layers of polyurethane-based foam and an 18-centimeter cylinder using a custom-designed cementitious material that behaves like concrete but cures faster. To understand why this matters, consider that ground-based 3D construction printers are physically limited by their own structure. A gantry printer can only build as high as its frame allows. A robotic arm can only reach so far, but a drone has no physical constraints on its vertical or horizontal range. The build volume is theoretically unlimited. The material science driving this technology is as sophisticated as the robotics. The concrete mixtures used in drone 3D printing aren't your standard sidewalk cement. They're precisely engineered formulations that must be fluid enough to extrude through a nozzle, viscous enough to hold their shape immediately after deposition, and strong enough to bear structural loads. Researchers developed 4 distinct cementitious mixtures specifically for aerial printing, each optimized for different flow characteristics and curing times. The material flows through supply tubes connected to the top of each build drone, feeding from external reservoirs that can be mounted on stationary platforms or, in some concepts, helium balloons that follow the swarm across the construction site. Meanwhile, in Hangzhou, China, a company called Dedibot was pursuing a parallel track. They unveiled a prototype called the Fly Elephant at TCT Asia in 2018, a hexarotor drone with a Delta-style 3D printer mounted beneath it. Dedibot's vision pushed even further into the theoretical. They claimed positioning accuracy of 0.1 millimeters in winds up to force 7 on the Beaufort scale. That's near-gale conditions. Their concept called for swarms of fly elephants working simultaneously on a single structure, each depositing different materials in a coordinated dance of robotic construction. The raw material would be supplied through tubes connected to floating helium balloons, allowing the drones to roam freely without returning to ground-based stations. The system Dedibot envisioned goes beyond anything currently operational. They termed their approach open-ended additive manufacturing, emphasizing that the only constraints on build size are the battery life of the drones and the material supply. No gantries, no rails, no fixed infrastructure limiting what can be built or where. The Fly Elephant could theoretically print structures underwater using waterproofed systems or in zero gravity for space construction. They explicitly positioned the technology for building on the Moon and Mars, where construction crews would be impractical and autonomous systems essential. Now scale this forward. Picture a factory floor unlike any construction facility you've ever seen. Instead of workers in hard hats, you see charging stations arranged in precise grids. Hundreds of drones sit dormant, their batteries topped off, their nozzles clean and calibrated. Massive mixing tanks along one wall produce continuous streams of the specialized concrete.
At the edge of
Formulation pumped into pressurized reservoirs. The digital model of a house appears on a central screen, its geometry already converted into flight paths and deposition sequences. The launch sequence begins just after dawn. First, the ScanDrones lift off, establishing the coordinate system and mapping the foundation. Their sensors create a millimeter-precise model of the build surface. Then, the BuilDrones rise, moving into position above what will become the front wall. The first layer of concrete emerges from the nozzles, thick as toothpaste, adhering immediately to the prepared foundation. Each drone deposits for precisely calculated intervals, then peels away as the next drone in sequence takes its place. The process resembles nothing so much as a ballet, or perhaps more aptly, a beehive. The walls rise layer by layer, each one bonding chemically to the layer beneath. Specialized drones with different nozzle configurations handle corners and window frames. Some drones deposit structural concrete, while others lay down insulating foam in the wall cavities simultaneously. The ScanDrones patrol constantly, their sensors detecting any deviation from the blueprint, alerting the central system to adjust the BuilDrones' trajectories in real time. Electrical and plumbing channels are built directly into the walls as they rise, following the integrated building model. Conduits emerge from the concrete layers, ready to receive wiring. Pipes trace their paths through the structure without any worker needing to drill through finished walls. Reinforcement comes through continuous fiber addition, with specialized drones depositing carbon or basalt fiber alongside the concrete, creating composite walls stronger than traditional construction without the delays of placing rebar by hand. By the 4th hour, the walls have reached their full height. The swarm reconfigures, with drones designed for horizontal printing moving into position overhead. The ceiling takes shape through a different technique, curved elements that span the structure like inverted arches, printed in overlapping segments that interlock for structural integrity. The roof follows, a thick layer designed to shed rain and resist wind loads, printed with integrated channels for eventual solar panel installation. By hour 6, the exterior structure is complete. Interior partition walls go up quickly, printed to accommodate electrical outlets and data ports in precisely positioned voids. The final 2 hours focus on finish work, smoothing compounds applied by specialized drones with spray attachments, sealing coats protecting against moisture, final quality scans confirming every dimension matches the blueprint. What emerges by sunset is a complete, watertight, structurally sound house. Not a shell requiring months of additional work, but a finished structure ready for door and window installation, for electrical and plumbing connections, for flooring and paint. The drones return to their charging stations as human workers arrive to complete the final 10% that still requires human hands and judgment. The implications ripple far beyond solving the housing shortage. Disaster relief could be transformed. When hurricanes or earthquakes devastate communities, the current timeline for rebuilding stretches into years. Imagine instead a fleet of construction drones deployed within days, printing emergency shelters faster than any conventional response could. Mobilize. The structures wouldn't be temporary. They would be permanent homes built where they're needed, when they're needed. The technology points toward even more ambitious applications. NASA has spent years studying 3D printed habitats for the Moon and Mars, and drone-based systems address one of the most fundamental challenges. You cannot send construction workers to another planet. ICON, working with NASA, has already built the Mars Dune Alpha habitat at Johnson Space Center, a 1/700 square foot 3D printed structure used for year-long simulated Mars missions. The same principles that let drones build autonomously on Earth could let them prepare habitats on other worlds before human crews ever arrive. We are watching the birth of an industry that will reshape how humanity builds. The construction drone market, valued at over $5 billion in 2024, is projected to exceed $20 billion by 2033. That growth isn't driven by speculation. It's driven by the fundamental mathematics of labor shortages, meeting housing demand, meeting technological capability. The question is no longer whether drone-based construction will become standard practice, but how quickly the infrastructure can scale to meet the need. Somewhere right now, in a research lab or a prototype factory, the next generation of BuilDrones is being tested. The concrete formulations are being refined. The autonomous coordination algorithms are learning from millions of simulated construction sequences. The future of construction doesn't look like anything we've seen before. It sounds like the synchronized hum of rotors. It moves with the patience and precision of machines that never tire, never make mistakes, never demand overtime pay. And it builds houses in 8 hours that will stand for a century.